Hello, everybody. Welcome to Fill the Glass, episode 19. I'm Carrie Millsap. Today, we're going to talk about Oracle microseconds. You might wonder, what in the world is that? Because aren't microseconds just microseconds? And the answer, of course, is no, they're not. This is all mentioned in the Mastering Oracle Trace Data book, by the way. On page 117, of the third edition of Mastering Oracle Trace Data, which, by the way, if you download the product, the book is in the Workbench product, so you can see all the updates that way. But this one is not recently updated. It's worked for a long time. So what we've done is logged into SQL Plus, and then I run this query to find out my kernel process ID. And that kernel PID is actually going to be the thing that we're going to strace in the experiment that I'm going to show you in a moment. So the strace command here is don't hang up. I want you to run strace. I want to see 132 characters in my strings. I want to output to a file called strace.txt, and I want to trace the process called 15197, which happens to be the kernel, the SPID, the system PID for my SQL Plus session. And then if I tail with a follow option, that strace.txt file, so this file name here is that file name there, then I will get stuff that looks like this. And you're thinking, oh my Lord, tracing was bad enough. Now I'm tracing, and I'm supposed to understand what's going on there. And yeah, that's what my talk is about today. So the fun thing about looking at strace output is that if there's anything you don't understand, you can read a manual page about it. So for example, if I want to know what get time of day does, I can just simply say man get time of day. I get a man page. And it tells me exactly what kind of things it returns and what kinds of pass by reference. You get a structure that's on the other end of a pointer when you call this thing. They're all just C system functions. So the way to read get time of day is if it succeeds, it returns a 0. And then these two numbers inside braces are the number of seconds and microseconds since the Unix epoch, which was January 1st, 1970 at 0:00 in the morning, Zulu time or UTC. So what we're seeing is the write to file descriptor 10, which is the trace file, of a string that says, wait, pound 13977, blah, 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 blah. And you can see the ELA value and all the things that you would see in a trace file, including the TIM. And you can see that there were 132 bytes written. And then you can see that there's another write to file descriptor 10 of just a new line character. And then you'll notice up here that, wow, Oracle didn't write the new line in the call that it made to write the string. So we've actually been living in the 10G, 11G world. And prior to that, with 2 write calls for every line that goes into a trace file, which is wasteful, but it's just the way that Oracle factored their code, probably for portability reasons. Because on Windows, they're not pushing a new line this way. They're pushing a 2-byte new line that's got a carriage return and line feed. And there's all sorts of little Easter egg type stuff like this that you can look through. If you spend an hour or two looking at this data, you'll see all sorts of little connections. So let me close that. That's the MOTD book, which you have with the product, or if you train yourself with our course at Thinkific, you get that book and that experience as well. So what we've done is we've traced an Oracle SQL Plus session that is itself tracing. And here's the kind of thing that we see. Here are a few lines from a trace file on line 50,078 that executes a get time of day call and then writes out a timestamp into the trace data and then writes the new line in a separate call. And I'll make a couple of comments here. Number one, get time of day. Basically, you can concatenate these two numbers as long as this one has 6 digits. If it doesn't, you have to zero pad from the left. But you can put a decimal point between these two numbers and come up with the number of seconds since the Unix epoch. If we look at what Oracle prints, it's the same as if we convert this black bold number that comes from here to a Unix epoch timestamp. And so there's a website called www.epochconverter.com where you can actually paste in this number and it comes back with that. And if you look, it's the exact same thing that Oracle printed out to the trace data. So that's cool. That makes sense. My numbers come from the operating system, and the numbers that show up in the trace match the numbers that the operating system returns. So that's all well and good. But there's another spot in the same trace file, and it's not very many lines later. It's just a couple hundred lines later. And what you can see is that Oracle's printing out a fetch line, and you can see 1079, and already it doesn't match this get time of day value. So why do we get a get time of day return value of 1105, but Oracle's printing 1079 and some stuff into the trace file? Well, here's what's happening. So the black bold number is only 14 milliseconds later than the first example. And you can see that the red number is not the same as the black number. So the red number comes from here. I just put a decimal point in, and the black number comes from here. But if you mess around a little bit, you can figure this out, that if you divide the black number by 1.024, you get the red number. That's kind of a cool little snap fit, isn't it? So what's going on is that Oracle's getting the black number from get time of day, and it's executing some sequence of operations upon it to transform it into a number that you can also get by dividing the black number by 1.024. And of course, you can turn it around if you'd like to, and you can say, well, if I multiply the red number by 1.024, I get the black number back. So these are just two ways of expressing the same relationship. So it's kind of strange. And at some point, if you care about things like this, you start to think, well, I wonder why they're doing that. And the honest to God truth is, I don't know why they're doing that, but I have a guess. My guess is that right around this era, and you notice you might have seen the subtle hint that this is a 10G trace file. It might be that on some platforms, just for the same reason that Oracle writes a new line in a separate write call, it may be that Oracle is dividing by 1,000 because on some platforms, the number that it gets from, and it's not get time of day, it would be a clock underscore get time, I think. It returns values in nanoseconds, in billionths of seconds. And in order to convert that into a microseconds time, which is what displays in the trace file, we would have to divide the nanosecond number by 1,000. Well, dividing by 1,000 is really expensive on a binary computer. It's really expensive, but it's super easy to divide by 1,024 because that's what a shift right operation, if you shift right 10 bits, it's as if you're dividing by 1,024. And 1,000 and 1,024, they're pretty much the same, so why not? So my suspicion is that the way the Oracle kernel is factored, because of portability reasons, back in the old days, they probably did the shift right of 10 bits to do the divide by 1,000. But then on some ports, they go, oh no, that number came from a microseconds domain, so we didn't need to have divided. So let's multiply by 1,000. And multiplying by 1,000 is not near as expensive as dividing by 1,000. So that's just a guess. It's semi-plausible. Could have happened. Maybe it happened. Don't know. But I can tell you that the numbers snap into place if you just start dividing them by 1.024. And now you can talk to your SA and go, okay, for whatever reason, Oracle's off by 2.4%, but that doesn't matter because now we understand where the numbers come from. You can trust that when I say something happened at time so-and-so, it really happened at time so-and-so. The nice thing is that on 19C, we don't have these things to worry about. And there are a couple of reasons for that. Number one is there are no system space timer calls anymore. And this isn't Oracle's doing, it's the advancements in Linux. It used to be that when we called get time of day, the program that called that would have to switch into kernel mode and then execute the call and then switch back into user mode. And you might get paged out or whatever when those switches take place, those context switches. So it's really cool that nowadays there are no system space timer calls anymore, which means they're faster than they used to be. So you'll notice in the trace file, there's not get time of day, get time of day, get time of day anymore. Linux has made the world a lot more efficient for us. So there's no system space timer calls. And you'll also notice that the new line is stuck in the same write with the content now. So yay. Now we're doing half the write calls that we used to do. And I think this probably changed either in 19C or 12C. I'm not sure, but it's good news all around. And you can see here on the fetches, there are also no system space timer calls. A couple of interesting stories. First off, the Mastering Oracle Trace Data book has this content in it. So if you're interested in taking that course, visit methodr.com on the training link, and you'll see all our courses there. So get time of day returns microseconds, but clock get time returns nanoseconds. And in order to convert nanoseconds times into microsecond timing, which is what's published in trace files, you have to divide by 1,000. But shifting right by 10 is a lot cheaper than dividing by 1,000. The problem is 50 years later, a 2% error is a whole year. So if we want to convert a TIM value to an epoch value, we're going to be off by a whole year if we don't do this divide by 1.024 thing. So this problem was fixed in 11.2, but oh my goodness, in 11.1, it was the worst version for Oracle tracing ever. Somebody saw in a C macro for printing wait line TIMs, they saw the logical shift right by 10 bits, and they said, computers are fast enough. We can actually give them the right answer. We can divide by 1,000. So they changed the wait line macro to divide by 1,000, but they didn't realize there was another macro that processed TIM values for DB calls, and it still did a logical shift right by 10 bits. So what was happening for a little while in 11.1 is we would see one TIM from the 1.024 domain, and we'd see another TIM from a divide by 1,000 domain. And so the TIMs were literally bouncing back and forth a year at a time. You'd see a wait line from this year. You'd see a DB call from last year. You'd see a wait line from this year. You'd see a DB call from last year. It was horrifying. So we had to write a utility to take care of it. And back in those days, it was called Mr. TIM Fix. But we added so many features to it that we actually retired Mr. TIM Fix and created a thing called Mr. 1011, which is our converter that'll take an Oracle 10G trace file and convert it into an 11G format so that our workbench can assimilate it. So that's my very long story about the Oracle microsecond. Like I said, it's a history lesson more than anything. It's kind of interesting maybe to understand that you can strace an Oracle kernel process and see how it interfaces with its operating system. So that kind of thing is still useful. But you don't have to worry about Oracle microseconds anymore unless you're still on 11G prior to 11GR2. You don't have anything to worry about anymore. So this was my show. This was Fill the Glass, a weekly podcast that I record live on Zoom. I'm Kerry Millsap. If you'd like to join us in the live broadcast, you can visit methodr.com/filltheglass for details about how to get here. And if you need help with performance of either your systems or your people, please reach out to us. We have software training and coaching. We can help.